So as it has been reported, the topic of my talk is about Lipschitz-free spaces. This is because all the 3 consecutive talks are devoted to the topic. And in my talk, I'd like to give some basic definitions, some introduction and survey to the area. And the other 2 talks will concern some recent results. So for the experts, this talk is somehow redundant, right? If they are not interested in recalling all the notions. So let me begin. So in our setting, we have a metric space with a distinguished point 0, which will be called as the origin in what follows. And we consider the vector space of all the Lipschitz functions, which are functions, real-valued one, which are Lipschitz and which preserves the origin. So it means that they map the distinguished point 0 from a metric space to the number 0. And if we endow this vector space with the norm being the smallest possible Lipschitz constant, then we get actually the structure of a Banach space. And we can consider the following evaluation operator. So it's really evaluation operator. It is given in such a way that any point is mapped to evaluation at the given point. And it is not difficult to compute that such a mapping is actually an isometry. And let me know that this isometry is not linear because on M we don't have any algebraic structure. But even if there was algebraic structure, for example, if M was a Banach space, then still this delta is not linear mapping. Well, and now I can give the definition of a Lipschitz-free space. It's just the closed linear hull of those evaluations, considered as a subspace of the dual of the space of Lipschitz functions. But okay, so this is the definition. It's not very difficult to give it. And however, it is very difficult to work with those spaces. But before talking about that, I'd like to say a few words about the importance of those spaces. So from the point of view of Banach space theory, or at least nonlinear geometry of Banach spaces, the crucial property of those Lipschitz-free spaces, and actually the reason why they are called Lipschitz-free, is the following universal property. So this is the following. If we have M row 0 as above, so it means it is a metric space with the distinguished point 0, then there exists up to isometry only one Banach space, which is actually the Lipschitz-free space defined on the previous slide, such that there is an isometry of from M to the Banach space, such that any point of this metric space is a linearly independent vector in this Banach space Fm. And moreover, those points are linearly dense in the Banach space. So this itself is quite a remarkable property that you can embed metric space into a Banach space in such a way that each vector is linearly independent. But moreover, those spaces have one more property, and this is the following. Whenever we have a Lipschitz mapping F, like here, right, then we can extend it to a linear mapping F hat, right, not enlarging the norm. So F is Lipschitz map, F hat is linear map, and they have the same Lipschitz constant. Or in other words, the operator norm of F hat is the same as is the Lipschitz constant of F. Okay, so there is one more condition which I didn't mention. This function F should map 0 to 0. Okay. So in particular, if we consider Z to be the real line, we can consider any Banach space. But in particular, if we consider the real line, which is of course a Banach space, then we see that any Lipschitz map, this is this line here, corresponds to a linear functional. This is this F hat here. So if one carefully writes that down, one reveals that the Lipschitz-free space has dual, which is isometric to the space of Lipschitz functions. So Lipschitz-free space is somehow canonical predual of the space of Lipschitz functions. It has this special universal property, and moreover, we have some construction by which we can work with those spaces quite effectively, or at least as effectively as possible. So let me mention one more consequence of this universal property. And this is that the Lipschitz structure of metric spaces corresponds to the linear structure of the corresponding Lipschitz-free spaces. So let me enlighten this comment. whenever we have a Lipschitz map F from n to n, like here, right, we can consider a picture, a diagram which is here. And now we consider the map F composed with delta, which maps M to the Banach space Fn, and make linearization. So we get a linear functional from Fm to Fn using the universal property. So whenever we have a Lipschitz map between M and N, we have a linear map between Fm and Fn. So in particular, for example, if M and N are Lipschitz isomorphic, which means that there is a Lipschitz bijection with Lipschitz inverse, then the corresponding Lipschitz-free spaces are linearly isomorphic as Banach spaces. So this is the remarkable property which itself enables us to provide some applications. So let me show one application which is well known nowadays. Okay. So this is the repetition of what I have written on the previous slide, and now the application. So Godfroy and Calton in 2003 proved that a Banach space X has bounded approximation property if and only if its Lipschitz-free space Fx has bounded approximation property. Okay, so application of this result is the following. We pick any Banach space with bounded approximation property, which is Lipschitz isomorphic to Y. I will not now recall what bounded approximation property is. It's not very important. The important fact is that it is some property dependent on the existence of certain linear operators. So it's preserved by isomorphisms, okay? Linear isomorphisms. So we have Lipschitz isomorphism between X and Y. And then since X has BAP, then Fx has BAP. We are applying this result by Godfroy and Calton here. Now, since X and Y are Lipschitz isomorphics, Fx and Ffy are linearly isomorphic. Okay. So we obtain that Fy has BAP. And then applying the result of Godfroy and Calton once more, we conclude that Y has BAP. So the conclusion is that the notion of BAP is preserved by Lipschitz isomorphisms, even though this property is defined by the existence of linear operators. Okay, so this essentially linear property is preserved by nonlinear maps. So this is somehow interesting. And actually this result motivated many researchers to study the Banach space structure of the spaces Fx. So let me finish this first. Okay. So, and there is one. So this shows you that there are some applications of this notion in the Banach space theory world. But there are also some connections to fields of mathematics which are outside of Banach spaces. And this is so-called transportation cost problems, Wasserstein spaces. So let me shortly describe this connection. So whenever we have a metric space, we say that a function is a transportation problem if it has finite support and some of its values are 0. So the interpretation is the following. For example, we have 7 cities, 1, 2, 3, 4, 5, 6, 7. And in each city, we have certain number which represents the number of bags of sugar which are needed in the city. So here in the first city, they need 3 bags of sugar, while in the fourth city, they have 4 bags of sugar, which they need to export. Here, 5 bags of sugar need to be imported, and so on. And then the solution to the problem F is to transport all the bags of sugar in such a way that we obtain number 0 in each city. Okay. So, for example, one of the plans is to transport 2 bags of sugar from the second city to the first city, 5 bags of sugar from the third city to the second city, and so on. And if you compute all the numbers, you get zeros everywhere. And the cost of this solution is just multiplying this number here by the length of the arrow here. Okay? So the contribution of this first arrow is 2 times the distance between the first and the second city. Here the contribution is 5 times the distance between the second and the third city, and so on. And if you compute this cost, you get somehow effectiveness of moving in this way. And the transportation cost norm of a transportation problem is the infimum of all the possible costs. Okay. And one can verify that if you endow the vector space of all the transportation problems with this norm transportation cost norm, then one gets normed linear space, and the completion is therefore a Banach space. And the connection is that this Banach space is actually isometric to the Lipschitz-free space. And the isometry is actually very simple. It's given by mapping each evaluation of delta by the characteristic function of x minus characteristic function of 0. Okay? And if you can extend it by linearity to isometry. Okay, so this is the connection. So let me conclude this first part where I gave the definitions, applications, and motivation. So the first remark is that Lipschitz-free Banach spaces, or maybe sometimes closely related objects, were introduced by many people and are known under a variety of names. Okay, some authors prefer the approach using transportation cost. Some authors the approach using evaluation maps. Okay, so for example, Nick Weaver calls them Arendt's yield spaces. Mikhail Ostrovsky calls them transportation cost spaces, and we do call them Lipschitz-free spaces. A closely related notion is the notion of a Wasserstein space. So this is a notion used in applications of mathematics quite a lot in PDEs and so on. So there is dedicated to the notion of a Wasserstein space a very long book by the field medalist Cedric Vellani. So there is a connection even to those works. However, in what follows, motivated by the work of Godfroy and Calton, we choose the term Lipschitz-free, and motivated by the applications, we investigate Banach space theoretical properties of Lipschitz-free spaces. So this is what we are interested in and what we study. So from the start of the theory, people were interested in BAP and related notions. So let me now recall the definition of BAP and related notions. So let me recall that a separable Banach space X has a Schauder basis if and only if there exists a sequence of projections such that the projections are uniformly bounded, they are finite dimensional, and the dimension of n projections is n. Here is this compatibility condition, and the ranges of the projections are dense in the space. And now we can weaken this notion of a Schauder basis in several ways. So the first weakening is to consider FDD, which is if in condition 2, you do not require that the dimension is prescribed as being exactly n, but you just require that the dimensions are finite. Right? Then we have the notion of pi property, where instead of this compatibility condition here, we just require that the dimension of images of projections are increasing. And finally, BAP, this is the notion I was talking about a few slides before. If you replace the requirement of having projections to having just finite dimensional operators. And moreover, if the projections are uniformly bounded by number 1, we say that the Banach space is MAP. Okay. So those are the notions, and all those notions are somehow related to the extension of Lipschitz maps. So let me give a brief survey on that. So when we have endpoints in a metric space and we have a linear extension operator, so it means an operator which extends the Lipschitz function from endpoints to the whole space in such a way that the Lipschitz constant is up to constant, not changed. Right? Then we know that there is a projection from the Lipschitz-free space M to a space linearly isometric to Lipschitz-free space over endpoints. Okay? And this is defined by just the adjoint and restricting to the space Fm. And the norm of the projection is the same as the norm of this linear extension operator. So in particular, if you want to build up the projections from the previous slide, so remember there were some finite dimensional projections, right? So the way how you define those finite dimensional projections is almost always through linear extension operators, like here. So the question is, when we are able to find linear extension operators from finite dimensional sets, or maybe good enough finite dimensional sets, and having as good compatibility conditions as possible. And in such a way, you prove that your free space has a certain approximation property. So let me now give some, or recall some results concerning Lipschitz free spaces and their approximation properties. So the first result I already mentioned is the one by Godfroy and Calton, who proved that X has BAP if and only if Fx has BAP. In order to prove this theorem, the authors had to prove first that the Lipschitz free space over finite dimensional space has metric approximation property. So this was actually kind of a lemma in order to prove this theorem, but it is interesting in its own as well. 11 years later, Peter Hayek and Eva Pernecka proved that Lipschitz free space over a little L1 and Lipschitz free space over finite dimensional space has Schauder basis, so the best possible notion we have. Moreover, using a result by Lancian and Pernecka, we know that if you take any doubling metric space, for example, a subset of Euclidean space, then the Lipschitz free space over this doubling metric space has pi property. Odd Dalet in 2015 proved that if you take Lipschitz free space over metric countable compact space, then it has MAP. Pernecka and Smith studied compact convex subsets of finite dimensional spaces, and they again proved that the corresponding Lipschitz free space has MAP. And okay, so one might wonder whether a Lipschitz free space over any compact space has MAP, but this is not true. There is a compact space, even a compact space which is zero dimensional, so it means it is homeomorphic to Cantor set, such that the Lipschitz free space does not have BAP and it does not even have AP, approximation property. With Doha, we proved that for ultrametric spaces, the Lipschitz free space has monotone Schauder basis. So monotone means that those projections are bounded by 1. And Hayek and Novotny studied Lipschitz free spaces over nets, which are aseparated B-dense subsets of certain Banach spaces. So they considered nets in C0 and CK spaces for K-metrizable. And nets in finite dimensional spaces, and in each of those cases, they proved that Lipschitz free space over this net has a Schauder basis. And quite recently, Doha and Kaufmann proved that Lipschitz free space over compact groups has MAP, and Michal Doha will talk more about this result later. So this is a kind of advertisement to the second talk. Okay, so that's it. So one might ask what is not known. So the first, probably the most important question in this direction is to determine whether for any uniformly discrete space, the Lipschitz free space has BAP. And the importance of this question is that if the answer is no, then it solves one famous open problem. And if the answer is yes, then we know something about any separable Banach space, which we didn't know before. So if the answer is no, there exists an equivalent norm, dual norm on L infinity without AP, but with AP but without MAP. And if the answer is yes, then the Banach space has certain property. Okay, all separable Banach spaces would have certain property. Let me note that the question is actually only about nets in Banach spaces. So here, one might consider, for example, nets in Banach spaces. So if you could prove that free space over any net in a Banach space as BAP, then you would be very close. Maybe even you would solve this problem here. So the second question, which is not so important as the one before, but also important, is to determine what is the best possible notion of approximation property we can have for Lipschitz free spaces over subsets of the Euclidean plane. So we know it has pi property, but we don't know whether it has Schauder basis. We don't know even whether it has FDD. And maybe even more important question is, we don't know whether it has pi property with constant independent on the dimension and norm in the finite dimensional space. And the reason why this is so important to answer is that it is closely related to the question of whether the notion of Schauder basis, FDD, or pi property is preserved by Lipschitz isomorphisms. So provided X has Schauder basis if and only if Fx has Schauder basis, we, as an application, similarly as in the BAP case, can prove that the notion of Schroeder basis, FDD, and pi property is preserved by Lipschitz isomorphisms. And the question here is related to the case of pi property here. Okay, so Godfroy and Carlton in their proof use that Lipschitz-free spaces over X as MAP, no matter what finite dimensional Banach space X you take, and something similar would be needed for pi property. Okay, so those are some results and questions concerning approximation properties. This was actually the start of the whole study, but nowadays researchers are interested in more topics than just approximation properties. And in the last 5 or maybe 6 minutes, I'd like to recall some areas of research which are seriously taken into account by researchers working in this field. So the first area which I pick is that for a given isomorphic or maybe even isometric property of a Banach space, we would like to find a metric space property such that a metric space has this property if and only if the Lipschitz-free space has the property of Banach space X. Okay, so like this. So we want to characterize those Lipschitz-free spaces having certain Banach space theoretical property. The most important in this direction is probably very recent result by Aliaga, Gartland, Petitjean, Procházka from 2021. And this is that M is purely one unrectifiable if and only if the Lipschitz-free space has Schur property, equivalently L1 does not embed into, and equivalently it has Radon-Nikodym property. So let me recall that purely one unrectifiable means that interval does not by Lipschitz embed into. Okay, so this is quite nice result. Second direction of research might be to investigate the structure of Lipschitz-free spaces over RD. So in this direction, let me recall that the Lipschitz-free space over the real line and over the plane are not linearly isomorphic, and it is open whether we have a similar result for dimensions 2 and 3. So this is probably somehow showing that the structure of Lipschitz-free spaces is very poorly understood. Even this non-isomorphism result is very difficult and relies on some summing operators and so on. Second important contribution, or I consider it important, is by me, Kaplitzky, and Kalendar from 2019, and this says that Lipschitz-free space over finite dimensional space is complemented in its bidual. The reason why we consider this question is that Gilles Godefroy noticed that if we were able to prove that Lipschitz-free space over little L1 is complemented in its bidual, then L1 is determined by its Lipschitz structure, which is a famous open problem, whether it is the true or not. Okay, so if the answer was positive for L1 instead of this finite dimensional space, then it would have a very nice consequence. So we studied at least finite dimensional spaces, and we proved that for finite dimensional spaces, at least we have this complementability in bidual result. But the proof was very difficult, okay? Or at least technically difficult. Another direction of research are so-called compact and bounded reductions. So in this respect, let me mention two recent results from this year. The first one is by Aliaga, Petitjean, and Procházka, who proved, for example, that Lipschitz-free space over a metric space M is weakly sequentially complete if and only if Lipschitz-free space over all of its compact subspaces is weakly sequentially complete. So since Pernecka and Kochanek proved that for compact subspaces of superreflexive spaces, we have that FK is weakly sequentially complete. As a consequence, we can see that free space over superreflexive spaces is weakly sequentially complete. So this is quite a nice result. Now, there are also some other compact reduction results concerning not weakly sequentially completeness, but also similar results holds for Schur property or for Radon-Nikodym property. And one more result by Albiak, Ansorena, Doucha, and me. This is that for any metric space, there exists a bounded metric space such that the corresponding Lipschitz-free spaces are linearly isomorphic. So, okay, so we don't know whether we can For example, at least for Banach spaces, replace bounded by compact. Okay, so this would be compact reduction of the optimal force somehow. Right? However, this metric space B is not a subset of M. It is just some metric space. Okay? So those are some results. And the last area of research is concerning isomorphic properties, is to investigate Lipschitz-free P-Banach spaces for P less than 1. To this topic, there were devoted recently 5 papers, and they have, and very often, okay, not very often, sometimes it is the case that if you have a new result for P less than 1, you have also new result for the case of P equals 1, which is the classical case. Okay, so this is one more. And concerning isometric properties, I'll very briefly comment on several areas. So the first one is embeddability of L1. So we nowadays know that Lipschitz-free spaces have some very nice properties of little L1, or maybe of capital L1, or maybe of produce of von Neumann algebras. So one might investigate this direction of research and considers other properties of little or capital L1 and try to see whether a Lipschitz-free space is inherits some properties of those spaces, at least in some cases. So for example, concerning embeddability of little L1, we always have little L1 complementarily embedded in FM, but not always we have little L1 isometrically embedded in FM. So one can somehow investigate quantitative version of this positive result here. Another is properties. People also investigate finite dimensional Lipschitz-free spaces. For example, in a recent paper by Alexander Fradelisi, Garcia-Lirola, and Zvavic, the authors proved characterized metric spaces for which the ball is Hanner. The ball in Lipschitz-free space is a Hanner prototype, and they investigated volume products and so on. So they considered questions attractive in the field of convex geometry. Right? Another is to investigate extremal structure of FM. For compact metric spaces K, Aliaga proved that any extreme point is the molecule, so it is of this form. And this is quite a famous open problem nowadays, whether the compactness may be dropped. Okay. And the last direction of research I'd like to draw your attention to is a result by Alega and Pernecka, and for bounded metric spaces, and in the full generality by Aliaga, Pernecka, Petitjean, and Procházka. And there the authors proved this intersection theorem. So if you take closed subset of complete metric space, then the intersection here is equal to the closed linear hull of the intersection here. Okay. So consequently, this enabled those authors to define the notion of a support as the smallest set, such that the member from the free space can be attained as a closed linear hull of the evaluations of this space K. And due to this intersection theorem, then we have that this point is the closed linear hull of delta of the support. So actually the support is then the smallest possible closed set, such that mu is the in the closed linear hull of all the evaluations on this closed set. And this notion of support seems to be somehow related to the notion of supports for measures, which enables us to study properties of those supports and hope that they would have some consequences for the structure of Lipschitz-free spaces. So maybe this will be somehow more explained in the third talk by Eva Pernecka. So that's all for now. Thank you for your attention.
Yeah, thank you very much. Thank you very much, Marek. I think we have some time for questions. So if there are some questions in the audience, well, you can either write them down in the chat or just ask directly. Well, in one of the results that you mentioned, although you did not really mention it explicitly, you have this nice result that the space of Lipschitz functions is the Banach algebra. Can you say something more about it?
Yes. Okay. So so that's true. This is related to this bounded reduction. So actually, if you endow a bounded metric space with pointwise multiplication, you get Banach algebra, but with the exception that the norm of the multiple of elements is less or equal than constant times norm of the multiplication of norm of two elements. However, this bounded metric space is so good that it actually enables you to transfer the pointwise multiplication from Lipschitz functions on bounded metric spaces to the unbounded as well, and it is very explicit. So the conclusion is, so this result is related to the conclusion, which is that if you endow the space of Lipschitz functions by multiplication, which is given by f times g, is fx times gx divided by 3 times the distance of x to 0. Okay, and if you endow this space of Lipschitz functions with this strange multiplication, you obtain the structure of a Banach algebra on the space of Lipschitz functions. So this gives you a very new example of Banach algebras, even for bounded metric spaces. So.
Okay, I see that we have a question from Niels.
This is probably a very naive question, but on your first slide, I think you said that if you start with a Banach space X as your underlying metric space, then delta X is not necessarily linear.
Yes.
Because I done some of these free Banach lattices recently, that's kind of surprised me, because isn't it simply the, if you like, the usual way you embed X in its bidual? Like
No.
you are,
No.
I mean, doesn't it follow from the fact that you add functions pointwise, or have I missed something?
No, it's very, very far from it. Actually, any point is linearly independent of each other. So for example, in capital L1, if you want to explicit description of this delta, then any point is mapped to characteristic function of the interval 0x for any point x. So this is explicit. Somehow
you're talking about the map delta,
yes.
The one that takes the point x to the point evaluation
Yes.
at x, not the point evaluation itself, right?
Yes, yes, yes.
Sure. Yeah, no, I see what you, I see what you're saying now. Sure.
However, it is known that for separable Banach spaces, x linearly isomorphically embeds into fx. For example, for non-separable C0 spaces, it is known that it is not true even that C0i does not embed into a Lipschitz-free space of C0i. Okay. So but this linear mapping is very non-trivial. It is not in any sense delta. It's just very okay.
Sure. No, thank you. Thank you.
Okay, I think that was the last question, because we will have another speaker in 3 minutes. So thank you, Marek, once again. Let me stop recording.
Okay,
thank you very much for this great talk. Okay, let me stop. Just a second.